All right, welcome back, everyone. So let me go ahead and start. So last time in 211, what we did was sorry, was there a question? Okay, so last time what we did was we talked about adding, subtracting electrons, creating charged bodies. But now we need to go ahead and quantify this, right? And we showed how we can generate a charged body and showed that on the electroscope. We did that at the very tail end of last lab, right? We went ahead, took that plastic ruler, we stripped off some electrons, we put it right next to it, and we showed that the foil leaves actually repelled each other, demonstrating that there was some movement of charge inside of the electroscope. Okay, now this was caused, the creation of this charged body, by adding or subtracting some E's. We took some electrons and we either took the electrons away, making a net positive body, or we added some electrons and made it a net negative body. Here's what we care about now, is how can we go ahead and quantify this a little bit. Okay, now we need to go ahead and give credit where credit is due. Charles Coulomb, a famous French physicist, is the one that discovered this relationship of charge. And I will briefly mention about Coulomb's law, but I need to put the name up here because in order to quantify this charged body, we actually need to use a unit that is named after this guy, right? So the unit is the Coulomb, and I'll write that in a second. But Charles Coulomb did all of this work from 1736 to 1806. So let's see, we're in 2020. 21, I guess. So go back 100 years. Okay, go back another 100 years. Okay, go back a little bit more and you're in Coulomb's time. Okay, so let's see. How do we do this? Well, let's go ahead and let's give ourselves a body. Well, actually, let's go ahead. Let's name the unit first off. Okay, we have the Coulomb, which is the unit of charge. The symbol is Q. Okay, so I can go ahead and take some body, and let's go ahead and say that this body is positive. And let's go ahead and say that this charge is Q equals, we'll go ahead and do 1C. Okay, so 1 Coulomb of charge on this body. Okay, what exactly does this mean? Well, what is 1 Coulomb? Okay, a Coulomb is represented by giving or taking away some finite number of electrons. Let me go ahead and write this up over here. 1 Coulomb of charge is an excess. So either we added a number of electrons or deficit we subtracted. Of how many electrons? 6.25 times 10 to the 18th. It's a ridiculously large number. Okay, so what does this mean? This body lost 6.25 times 10 to the 18 electrons. That's my abbreviation for electrons. E's minus because they're responsible for giving a negative charge. Okay, and the same thing if we were to have a net negative body. Let's say this guy is negative, but let's say now that he's got a charge of 2C. Well, what happened? Well, he gained some electrons, okay? So normally, before, when he was neutrally balanced, he had 1 proton for every electron. And they're balanced out, right? It was a neutrally charged body. But somewhere he became a 2C, a 2 Coulomb charged negative body. Well, he became negative because he somehow got a bunch of extra electrons. And specifically, he gained 2 times 6.25 times 10 to the 18 electrons. And that's all there is to it. Okay, now let's go ahead. Let's take this a step further as to what Charles Coulomb says about this relationship of coulombs and force. I guess any questions about this? Hopefully that demystifies some stuff. If you have questions, feel free at any time to type them into chat. I will check there periodically. Okay, now, what does this lead to? Well, we're going to have some attraction or some repulsion due to these charged bodies. That's kind of the idea here. So let's go ahead. Let's take 2 bodies. Let's give them some charge over here. Wah, wah. Okay, so we got a positive body. We have a negative body. Well, basic law of charges we discussed last time, they're going to go ahead and attract. So there's going to be some force. Okay, and we know that since these are charged bodies, they have some amount of coulombs that they have lost or gained, right? It's got some charge. Okay, so here's what Coulomb's law is. Force equals some constant times the charge of Q1 times the charge of Q2 divided by the distance squared. Okay. Well, what does this mean? The force and distance are inversely proportional, so the closer they are, the stronger that attraction would be, or that repulsion would be. In other words, the stronger or the force would be. And F is in newtons. K is a constant. 9 times 10 to the 9 for air or vacuum. Q is charge in coulombs. And D is distance. Between the charged bodies. in meters. Distance between charged bodies in meters. Okay, this is Coulomb's law. This is how the problem would be set up. You plug it into this equation, you use these values, you get your answer. This is the only time I'm ever going to show it in this class. We're not going to use it to calculate anything, nor am I even going to do an example of it. And I'll even tell you, you don't have to memorize this for a exam or anything. Okay, so I'm actually just putting this up there for completeness and to give credit where credit is due, because charge really is the beginning of our story when we're talking about electronics. Okay, so this part's important. This is good to know, but we're not really going to use this when looking at electronic circuits because we're dealing with wires and resistors and components, and this has nothing to do with any of those really. But yet it does. It's the beginning of everything, okay? So let's go ahead. Let's continue. And let's go ahead and set up what is going to turn into our first very useful circuit. All right, what's the deal with talking about all these charged bodies? Why did I even take the time to go over that? Well, let's look at a battery. We know that batteries power all of our electronic devices, so there must be something going on in there. Here's my battery. It could be a AA, a D cell, a C cell, whatever it is. At the top, this is generally labeled as positive. And the bottom is labeled as negative. As this battery sits here, notice something about it. It's got an imbalance of charge already internally created to the battery. It's got some positive charge at the top. It's got a negative charge at the bottom. In other words, excess electrons here, lack of electrons here. Okay, and as this sits here, it does nothing until we provide two things. Something to do work on, we will call this a load, and we need a way for electrons to move through the thing that we want to perform work on. Okay, so we got a battery with an imbalance of charge. We have some transportation, some wire, something that can conduct electricity, just like I talked about before. Last class, remember, one valence electron in something like copper. Very easy to move an electron out or add an electron to that valence electron, that outermost shell of the atom of copper. And so copper makes for a really good transportation of electricity. Now we have something that we want to put electrons through, okay? Now check out this. We have an excess electrons, we have a lack of electrons. These electrons want to go from here to here. The electrons want to go home. Now, they can't do it internally in the battery for some reasons that I'm not going to get into. They have to take the long way around, okay? So we're going to get E's. I want to use a different color for E's, but I already used black for, okay, fine. E, 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 see what's going on? So the E's are going to go through our load. They're going to come out of the load. E, E, E. They're going to return home back over to this side that has a lack of electrons. They're going to be so happy because now this battery is becoming balanced. That's what they wanted to do the whole time. These E's just wanted to get from this side over here. But we said, no, you don't get to do it for free. We're going to put something in here and you have to do some work for us before you get to go home. So that's what's going on. We are making a path for the electrons to make their circle, make their travel, but we're not going to let them get away for free. We're going to make them do something for us. This could be a light. This could be a computer. This could be your phone charging it. It could be anything, okay? This is just a load, something we want to do work on. And it's all created by this imbalance of charge. So that's the first thing to know. It's the imbalance of charge that starts everything. Now we have a name for this imbalance of charge. We call it the electromotive force. The electromotive force is the force created by a difference of charge. Okay. Force created by a difference of charge. We have a difference of charge. We have an electromotive force. We can measure this electromotive force. It is the volts. Now we're getting to stuff you've heard of. The volts, the voltage, okay? When we're saying volts, we are saying the electromotive force. Electromotive force you may also hear as an EMF, okay? So EMF, volt, voltage, they're going to be used almost synonymously with each other. Now, if you're a real stickler, you're going to say, no, the volt is the unit of electromotive force. Whatever, tomato, tomato. Volts, voltage, electromotive force, for all practical purposes, these are the same thing. It's the force that this battery is imparting upon the circuit by nature of having this imbalance of charge created internally. And the symbol that we will use is V. Now you're going to see some textbooks that will use E for voltage. You will see some Europeans use E for voltage. You may see some physicists do use E for voltage. There's nothing wrong with any of those. They use E instead of V for voltage because they're talking about EMF. And so they're saying, well, it's an electromotive force, so it's E, it's not V. But the unit is volts, so V. It doesn't matter. E or V are both valid in this world. However, for this class, for me, and for a lot of data sheets and manufacturers, V is going to be the letter that we use. I find V to be a little more practical in industry as far as data sheets and manufacturing goes, and stuff like this. And at the end of the day, we're looking to get jobs in engineering, at least the vast majority of us. So I try to stay a little more practical. Okay, so are there any questions about this? There will be a question of, well, what's 1 volt equal to? I can't answer that yet. We're going to have to learn a little more. It actually relies on a different definition. But for now, know that V is our first quantity of interest. It's the electromotive force, and it's created by the imbalance of charge in whatever device is powering our system. Okay, so let's go ahead and let's continue with this. We need to discuss movement of charge. And what I want to do right now, before I get into movement of charge, let's go ahead and let's take... Oh, no. It's 9... Sorry. I'm looking at the time. We started at 9:30. So we still have... Yeah, we still have what? How many minutes? 30 minutes? Before we should have like a 10-minute break? Yeah, okay. Sorry. I'm getting ahead of myself. Okay, we need to go ahead and discuss movement of charge, right? Because I said, hey, this is the voltage that's creating the movement of charge, but we need to describe this motion, right? So we only kind of described what quantities we're going to use for this device. We still need to talk about how these things move around in this path. Okay, so this section is going to be titled Movement of Charge. All right, so as we saw, we're going to cause these E's to move around. So let's just imagine that these E's are a bunch of marbles, and let's imagine that this wire is a pipe. Now, we caused this situation to occur by having something more negative on this side and having something more positive on this side, right? So having this imbalance of charge created a force of EMF, or voltage, So you can think of my finger pushing a bunch of these marbles in a pipe. My finger is the voltage. And the imbalance of charge caused my finger to push on these marbles. And these marbles are now moving through a pipe. Do we have a small number of marbles or do we have a large number of marbles? Do we have a large pipe? Do we have a small pipe? This is what we're getting at when we're talking about movement of charge. Okay, so how many of these marbles? How many of these electrons? So how do I quantify this? All right, we're going to call the flow rate of these electrons a current. Now, the unit of current is going to be the amp or the ampere. The symbol that we're going to use for current is going to be I. And now we need to go ahead and quantify what 1 amp is. 1 amp of current. Is that a lot of marbles? Is that a little bit of marbles? We're going to go ahead and describe how many of these marbles are moving using a definition. A flow of 1 coulomb. That charge is coming back, right? Makes sense because a coulomb is equal to a finite number of electrons, 6.25 times 10 to the 18, right? A quantity of electrons, a flow of 1 coulomb per second equals 1 ampere or 1 amp. Okay, so a flow of 1 coulomb per second equals 1 amp. Okay, this is how we're going to go ahead and quantify a current. We're going to say the current is I is equal to some number of amps, and that 1 amp is equal to 1 coulomb per second. And if you feel like this is a little confusing, I'm right there with you. So let's go ahead, let's describe this a little more in detail. Okay, I'm going to break this up into 2 different ways of the same thing. Okay, so on the left side, I'm going to say 1 coulomb per second equals 1 amp. That's what I just said. 1 coulomb is equal to 6.25 times 10 to the 18 electrons. If you're stuck with coulomb still, think of the word coulomb as like saying a dozen of something, right? If I say a dozen of eggs, I have a dozen of eggs. How many do you have? 12. If I have 1 coulomb of charge, I have this very large number of electrons, right? It's just a finite value, a finite number of something. Okay, next up on this other side, I'm going to give you an equation. I, current, equals charge Q over T, time. Okay, time's in seconds. Actually, let me start with I. So current in amps, Q charge in coulombs, and T, time in seconds. Okay, these two are the same thing. 1 coulomb per second equals 1 amp. 1 amp equals 1 coulomb for 1 second, right? Okay, 1 amp equals 1 coulomb for 1 second, right? Here's the easiest way to think about this whole definition of current. Imagine I have a wire with electrons flying through it. My electrons are moving in, let's say, this direction. And I am standing here. As a stick figure holding a little clock. And I have some type of superhuman vision because I can see right into this wire and I can actually watch these electrons whizzing through. And I can just sit there and I can count them. I'm going to start this timer. Tick, 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 tick. And I am going to stop that timer after 1 second. And during that 1 second, I'm going to count how many electrons flew past this one point of this wire. Right? You see where I'm going with this? If I count 6.25 times 10 to the 18 electrons in 1 second, I have 1 amp. And that's all there is to it. Okay, so I sit there, I start my timer, and I stop that timer after 1 second. And during that 1 second, I picked the point and I counted how many electrons I saw whizzing by. And yes, I counted a very large number within 1 second. Like, this is not humanly possible, but I did. And since I counted 6.25 times 10 to the 18th, since I counted 1 coulomb of charge in that 1 second, I got 1 amp. Okay, is this good? Is everyone all right with current? Thanks. Okay, so let's go ahead and let's keep going with this. We're actually almost done with our quantities. We only need one more. And the last one is resistance. Okay, so to recap, what do we got thus far? Well, check this out. I'm going to go back to my basic circuit drawing. This is the simplest circuit you're ever going to see. We have V for voltage of the power supply. We have the electrons in the wire and the flow rate of those electrons that we are calling I. And we got one piece of the puzzle left. We have the thing that we were going to do some work on, which will have some resistance, R. These are things like light bulbs, laptops, cell phones, things that use electricity, things that you may have to charge, microcontrollers, processors, everything that is electronic is a load and has some resistance R. So we're going to go ahead, let's talk about R. I like to think of resistance as molecular friction. It's just like something like sandpaper. It's harder to move across. It provides some friction. Okay, now we need to go ahead and talk about the factors of resistance because different things affect resistance. Okay, the first one is material type. Maybe my material does not have one valence electron. Maybe my atoms comprising a material has 2 valence electrons. Maybe it's a little harder to move those valence electrons around. So my material type can have more or less resistance. Am I going to get less resistance than a wire? No, a wire's already got 1 valence electron. And yes, somebody can type into chat, superconducting blah, blah, blah. Yeah, sure, you're right. Okay, you can make it superconducting. That being said, in normal everyday temperatures, you're not going to get much better than one valence electrons, something like silver, copper. Those things are going to have the least amount of resistance. Okay, so material type can definitely add to this idea of molecular friction. Okay, this one's really obvious to see. Size of the conductor. If I make a wire smaller, it's going to have more resistance. This is so intuitive. It's exactly what you're imagining. I just created a bottleneck, right? And there's so many ways I can do this. Here's some thick wire. There's my top example. Here's my thin wire, right? Here's my bottom example. Clearly, one of these has more friction, more resistance per foot than the other, right? Okay, so the size of the conductor or the material type. I can influence and change my resistance of materials in those two ways. All right, I got one last one. This one's fun. Temperature. Okay, turns out resistance changes with temperature. Usually, generally speaking, most materials that are good conductors will actually increase in resistance the larger the temperature is. Higher temperature equals more resistance. Okay, now why is that? Well, think about it this way. If you have some material with a bunch of electrons floating inside and they are just sitting there at a very happy, chilled temperature, it's very easy to move those and cause them to move within the material. However, the higher the temperature is, the more energetic those electrons are on the inside. And that makes it actually a little harder to get them to move. Okay? So usually most conductive materials, higher temperature equals more resistance. Somebody usually asks, well, why would then sometimes with some materials does lower temperature equal more resistance? And this is very true. We actually have positive coefficient temperature, positive temperature coefficient materials and negative temperature coefficient materials. If you have something like a semiconductor, which is on the verge of being conductive, but naturally does not really want to be conductive, right? So if I have something like 4 valence electrons, those are stuck there. They don't really want to move. But if I add some energy into the system, much like heating it up a little bit, then I can get them to wiggle a little bit more, and that'll actually cause an action more like freeing of those electrons, and would actually allow them to pop and move inside of your material more easily. Okay, so some materials will have less resistance with higher temperature, and some materials will have more resistance with higher temperature. Okay, I just want people to be aware. Material type, size of the conductor, and temperature are your three primary methods of influencing and affecting resistance. Everyone cool with that? I'll take a yes in chat. Okay, and I'm definitely not going to quiz or test or ask any questions related to positive or negative temperature coefficient materials. Well, let's be honest. I think I only learned about that well, it's been a little while now, but okay.
I have a quick question.
Yeah, what's up?
So like in something like metal, where like when it gets cold, it like constricts.
Uh-huh.
Is that what you mean by like something that might be affected? Because in that case, when it be a smaller area for the electrons to travel through?
Okay, I
Or
see
more
what you're saying.
compressed?
Yeah. Keep in mind, if you're talking about just like a material shrinking because I stuck it into the freezer, that amount of shrinkage is very, very little. So that's
Oh,
not the same that I'm saying with temperature. When I'm talking about temperature affecting resistance, I'm actually saying that on the molecular level, not really at the macroscopic level. Because if you're talking about your material actually shrinking a little bit, yeah, it's going to constrict. It constricts like from a chunk of metal like this to a chunk of metal like this. It's very small, right? But internally in the structure of those atoms, these electrons, if I were to increase the temperature inside, those electrons are wiggling a little more. So it's really more of a wiggling of the electrons than it is a physical changing of the size of the material.
so it's like trying to navigate walking through a dance floor as opposed to everybody just standing around.
Yeah, totally. Just like trying to navigate a busy club, right? You got a bunch of people just like doing this and getting in your way. I love the analogy. That's perfect. Yes. Yeah, in fact, I'm going to make a note of that and I'm going to use that next time because I love that. Yeah, it's just like it's a bunch of just people like in a dance room getting in your way. Or a mosh pit. I don't know. What kind of music are you guys into?
Mosh pit is adequate for me.
Perfect. Well, thank you so much. Okay. So yes, okay, these are the factors that affect resistance. We haven't quantified it yet. So let's go ahead, let's talk about that. Resistance is the molecular opposition to the flow of current. Duh. Okay. Right? That's what I've been talking about thus far. This guy is impeding the flow of current that these electrons are doing through it, right? The unit of resistance is the ohm. And the symbol is the ohm symbol. Okay, so we have resistance, ohm, and symbol, right? Okay, so let's go ahead and we need a definition for resistance. An ohm of resistance is the amount of electrical resistance that limits the current to 1 amp when 1 volt of EMF is applied. Okay, an ohm of resistance is the amount of electrical resistance. It's a little facetious. Okay, an ohm of resistance is the amount of resistance that limits the current to 1 amp when 1 volt is applied. Okay? There is a much easier way of this jumbled sentence. It's called Ohm's law. And Ohm's law is beautiful, and we are going to use it every day for all of 211 and for all of 311. We're going to take a break after I show you what Ohm's law is. We're going to come back to the lab. We're going to talk about Ohm's law some more. We're going to do some examples with Ohm's law, and then I'm going to do a lab and show you Ohm's law in action. Okay, let's go ahead. Let's put Ohm's law in all of its glory on this board. V equals IR. V is for volts. I is for amps. R is for ohms. Okay? I just remember it like this, ver. V equals IR, ver. And it is this exact sentence written in a much more condensed, I think, easier to see equation. And since we are using this equation all day long, every day, we might as well just look at this. An ohm of resistance, 1 ohm. Equals, now notice I'm changing this equation around, right? So I'm saying 1 ohm is equal to something. I'm saying R is equal to something. So R is going to be equal to V over I. Let me write it up here. An ohm of resistance is the amount of electrical resistance that limits the current to 1 amp when 1 volt of EMF is applied. Okay? The definition of a volt and resistance are reliant upon each other. 1 coulomb is pretty easy to understand. I sit there and I count 6.25 electrons fly past, 6.25 times 10 to the 18 electrons fly past my face in 1 second. That's 1 amp of current. If I have 1 volt with 1 volt of force applied to my circuit, 1 volt and I have 1 ohm, I get 1 amp. Okay? We're going to play around with this when you guys come back. So let's go ahead. Let's take a 10-minute break. We're going to be back at 11:36. I'm going to write it here, but don't put this in your notes. Don't ruin this beautiful equation right here. 11:36 a.m. Okay, let's be back at this time. Don't forget, notes are due by Friday, 11:59 p.m., including things that we cover in lab today. Okay? So that'll be due. Also, if you haven't done the loan agreement, do the loan agreement. No, it's not an hour break. We have an hour break? No. Am I wrong on that? Sorry. I'm looking at chat. I'm like, we have an hour break. I'm like, no, where'd you get an hour break? I wrote it that way. Okay. My apologies. Okay. So yeah, don't forget, loan agreement by today, 1 hour after we're done with lab. Please don't take up lab time to do it. Wait till after the lab and then go ahead and do the loan agreement if you haven't already. I need those. And I'm going to submit them today, and I have to submit them today. So I don't have time to wait. If you forget, too bad, I'm going to say. And then notes are due on Friday. Okay? All right. So let's take that 10-minute break. We will now be back at 10:38. All right. See you guys. Okay, welcome back, everyone. So let's go ahead and let's continue. Let's clean up a few things. Sorry, give me 1 second to respond to a chat message. Okay. So let's clean up a couple of things here. So we have something causing our electromotive force, causing these electrons to move around. That flow rate of these electrons is our current I. The electromotive force causing the electrons to move in the first place is our voltage. And the thing that we are putting in its path that we want to make these electrons do some work for us is going to be our resistance. Okay, and this is a perfectly valid way to look at this. However, this is not proper schematic terminology. So let's go ahead, let's fix this. This guy over here is representing a voltage source. Okay, for a voltage source, for now, we will use this schematic symbol. Now notice for our voltage source, the larger side is our positive, and the smaller side is our negative. And let's go ahead, let's just give them a value right now. Let's get this over with because we're going to see it like this over and over and over again. Okay, V refers to this part, and we're saying that V is equal to 10 volts. Okay, and this is the schematic symbol that we're going to be using. And that's all we need to do. Now let's go ahead. This resistor, now this actually is a correct symbol for a resistor if you are in Europe, but we're not in Europe, so I'm actually going to change it. Resistors in this class are going to be written as this. Okay, if you think about it, the symbol for resistance looks like the electrons are going to have a hard time navigating around these sharp corners, hence why it's getting used that way. Okay, let's go ahead and let's give this a value. R of this resistance is equal to 5 ohms. Okay. Now we need to pick a direction for our current. And I know this one is going to be a little painful here. The electrons are moving in a counterclockwise fashion. Yes, these electrons are moving in this direction. And in this circuit, the electrons are moving in this direction. Absolutely. We call this electron flow. Now, historically, we knew that there was an imbalance of charge. We knew that something responsible for this charge was moving, but we did not have the technology to tell us that it was the electron and that the electrons were moving in a specific direction. We just knew that something was moving. We didn't know if it was going clockwise or counterclockwise. We had a 50-50% chance of getting this right, and we picked the wrong side of the coin. Current, therefore, for the rest of the class, for today, for the rest of 311, for the rest of your industrial careers, or consumer electronics careers, or electrical computer engineering careers, current is going to flow from positive to negative. We call this conventional flow. There is nothing wrong with picking the current to go in this direction. Yes, it's not the direction the electrons are moving, but it's okay. This works the same. There is no difference. Here's why we're going to stick to conventional flow. You remember when your parents told you, if your friends jumped off a bridge, would you jump off with them? Anyone ever hear their parents say that? I know mine did. Right? Yeah. If your friends jumped off a bridge, would you jump off a bridge with it? Yes. Everyone else is jumping off this bridge and we're going right with them. Conventional flow is what we're going to stick with. Okay? So manufacturers stick to conventional flow. Electrical engineers stick to conventional flow. The only screwy people on the planet that like to go like, no, the electrons are going in this direction, we need to stick with that, are physicists. And we don't care what the physicists are doing, okay? Physicists are great. I love physicists, but they're not designing things, okay? We have to live in the real world. And we have to live with what the manufacturers are telling us. So we're going to stick to conventional flow. But we will keep in mind in the back of our heads that the electrons are not going in this direction. The electrons are going in this direction. Okay? There was a question. Would your numbers become negative if your reference was from the perspective of electron flow, but you would still get the same numbers? Yes. Yeah, right? Negative charge is moving in this direction, positive charge is doing in that direction. Yeah, you would if you go ahead and solve a problem that was laid out to be done in electron flow, but instead you took the convention that the current went in the other direction, that just pops up as a minus in your current. That just means the current is flowing in the other direction. Okay, so it's not a big deal. Okay, so we're going to go ahead and stick with this because everyone else does it this way. It's just going to make life so much easier. Okay, that being said, for my whole story up to now involving quantities, I've wanted to stick with the tangibleness because you can physically imagine those electrons moving through the wire. So I stick with it like this up to now. And then I go ahead and I throw this bad coin toss at you that just historically we got it wrong, and nobody wants to go back through our whole history and change that. Okay, so conventional flow, current's just going to go in this direction. Perfect. We got everything set up here. Let me go ahead and let me just clean up my electron flow versus conventional flow. I will be asking a question like this on the exam. What's this one? Say it in chat. And what's this one? Say it in chat. And which one are we using? Because everyone else does. But the electrons absolutely are physically moving in this direction. Okay, let's go ahead, let's fix, and let's go back to our original numbers and our schematic, and let's go ahead and solve out Ohm's law for that. And before I do this, let's take a minute because this might take a little bit of time, and I'm pretty sure most people probably did not download Ltspice already. Let me take a break from this for 1 second just so that this can be going on in the background. I forgot my own website for a second. Okay, make sure you go to my website. Go to 211. Go to Ltspice. Right-click, save link as. And save this zip file somewhere. It's going to take a little bit of time to download. So I just want this download to go on while we are discussing Ohm's law, because we're going to go ahead and open it. Now, I had said this last class, please download the zip file. But if you haven't, now's a perfect time to start. Okay, so should have downloaded it. Let me know if it has not finished downloading for anyone. Mine downloaded in like 2 seconds. I guess internet speeds are a lot faster than I give them credit for these days. Did everyone get it? Say yes if you got it.
I got it.
Perfect. Awesome. Okay. Okay. So you downloaded it. You probably downloaded it to your download folder. Okay. So go ahead and navigate to the folder where you downloaded it. Okay, the easy way to navigate to that folder is in the lower left-hand corner. If you still have the Ltspice in your browser that popped up, you can right-click on it, and it'll say, it'll give you an option to navigate to that folder, open in folder, something along those lines. So that's the easy way. Or you can manually go there through the file browser. Either way, you want to have a file browser open where you can see the file you just downloaded. Okay, everyone see how I have this? You want to make sure that you extract this. The extraction is what's going to take the most amount of time. Right click on it, and you can hit extract all. And it'll ask you, where do you want to put it? And you can just extract it to wherever the default is and run it from there. There's no problem with that. So that's one way. You can just right click on the zip file and hit extract all. If you're using another program for decompressing, then sometimes you have a context menu for that. Like I use 7-zip. You can use 7-zip to extract it to a specific location. You can also right-click on the zip file, right-click on it and hold, and drag it over to an empty spot of your window and let go. And then the same thing's going to happen. It'll give you some context menu. You can just hit extract. And again, it'll give you the window to extract to that specific file or folder or directory. So however you want to go ahead and do it, but you must extract this. You cannot, don't do this. Don't just double click on that. It looks like it's open, right? It looks like it's open. And if you go ahead and you do this, it's going to work, and then it's going to not show you all the components. And then half hour into it, you're going to go, but like Eric Hernandez, I don't see the components you're telling me to. A reason for that is those components need the extraction in order to be visible. Okay, so if you want this to work, absolutely have to right click, drag, let go, and extract, or right click and extract. Okay, that'll take some time. I'll do it right now. Okay, there's a lot of little files, so it's going to take like a good 10 minutes in order to do this, especially on some people's computers. Okay, so leave this running in the background and go back to the Zoom window, and let's talk about our Ohm's law. Now that I did my zooming in, I got to fix that. Okay, there we go. All right, sorry about that. All right, so let's go ahead and let's set up that same example that we had before. V is equal to 10 volts. R is equal to 5 ohms. Conventional current, remember the bigger side is positive, the minus side is the little side, and conventional flow says current's going to flow from positive to negative. I is equal to what? Now, if you notice from our equation, V equals IR, I got over here, I got 3 quantities. 1 is unknown and 2 are given. I always need to have 2 knowns and 1 unknown in order to solve this equation. Okay. Now, yes, Kyle's got that, right? It's 2 amps, obviously. Okay. Now, there's a couple of different ways I could do this. I can go ahead and rewrite my expression for what it is that I'm looking for. I got a question mark in I, so I can just say, what is I equal to? And I can rewrite this. So I can say I is equal to, well, I got to divide both sides by R, so V divided by R, okay, and then I can go ahead and plug in my values. V divided by R, 10 volts divided by 5 ohms, equals 2, what? Notice I'm putting all my units. Volts is always in V, ohms is always in ohms, and I is always in amps. So my answer is 2 amps. Okay, everyone good with that? Okay. So for Ohm's law to work, I always have to have 2 of my 3 given. Okay, so check it out. 20 volts of EMF applied, 20 volts of our voltage source applied to the circuit, causing 5 amps to go through it. However, I don't know what the resistance is. Can I calculate it? Absolutely. I got 2 of the 3. So what's R equal to? Well, again, V equals IR. Okay, so what's R equal to? Rewrite the equation. R equals V divided by I. Okay, what's V? 20 volts. I, 5 amps. So R is equal to what? 4 ohms. And it is that easy. I believe the answer is you can just leave it as is. Although I have to ask something in chat. I've never heard of that before. Okay. Now let me go ahead and kind of express a few things about this situation in the schematic. If I have 5 amps going through here, I have 5 amps going through here. If I have 5 amps going through here, I have 5 amps going through here. Okay, remember that current is flowing through a path. So let me go back up to this upper example again where I solved it, and let me do another one. And let me go ahead and start playing around with the symbols here. I may have more than one voltage source. At which point I might write V subscript 1. And then if I have 2 voltage sources, V subscript 2, V subscript 3, V subscript, etc., right? So V1 is equal to 10 volts. Perfectly legit way of writing this out. Okay, my resistor over here, I may have more than one resistor, at which point I would start saying R1, R2, R3, R4. Again, playing around with the subscript. Subscripts are free. You can call a subscript whatever you want. I can say R1, 2, 3, 4, 5. I can say R hello. I can say R whatever I want. Each subscript just refers to a different resistor. Now, if I left the problem like this without saying anything, I R1 equals, right? See what I did there? I, the current going through R1. Okay, that's all I'm saying there. If you notice, this one was made up. This one was made up. This is not made up. This is kind of like, this is being driven. Like the subscript is being determined by where the current is going through, right? So if we're going to be very specific, as we should be if we're going to be a bunch of engineers, we're going to go ahead and label things properly. So IR1 is always going to refer to the current going through R1. If I called this R hello, this would be IR hello, right? Okay. This is proper industry accepted nomenclature for labeling of components in a schematic. This is my point. We're going to start here with the right way of doing things as we would see them in the workplace. At this point, now I can go ahead and say, well, what's IR1 equal to? Well, we know that V equals IR, so I is going to be equal to V divided by R, right? Okay, so IR1 is equal to 2 amps. Everyone good with this? Cool. Okay. That's Ohm's law in a nutshell. I solved for I, given that I know V and R. I solved for R, given that I knew I and V. I guess I didn't solve it the other way, but 2 of the 3 that are given, you're going to be good. Okay. So let's go ahead and let's do a simple Ohm's law in the Ltspice modeling software. What time is our class over with? Type that in chat. Do we have time for this? 11:45. Good. We have just enough time. Okay, once you are done with the extraction, you're going to navigate to that folder. And you're going to run one of 2. There's an x64 and an x86 executable. Let me go ahead, type these into chat. Run either one. It doesn't matter. If you are on a 64-bit architecture, which almost the entire class is probably, then you're going to run the x64. That's perfectly fine. If you run the x86, it's going to be fine too. The only issue that you would possibly have is if you were on an x86 architecture and you try to run the 64-bit version, at which point it'll complain to you. But I can almost guarantee that everyone here is on a 64-bit computer, so just run the x64 version. Okay, either one of those. Once it runs, it should look like this. Okay, so I'm going to give a little bit of time while I adjust my screen over here so I can try and zoom in on this maybe a little better. But everyone, you should get to this screen where you just ran up Ltspice for the first time. It may decompress some things on your computer. Don't update. No, if you did, it's okay, but don't. I get the feeling update is actually going to overwrite some of my components that I created. It won't affect much in this class. It may affect something in 3.11. If it's too late, don't worry about it. No big deal. If you hit update, don't even sweat it. Not an issue. Okay. But if you haven't done it yet, right, then don't update. I don't think it's a big deal either way, to be perfectly honest. Oh, that's the problem. It doesn't give me the file window at the top when I do it this way. That's what I had trouble with last time. I'm always trying to figure out a way in OBS Studio in order to zoom in on certain parts so that people can see the text more easily. I haven't figured out a good way to do this yet, aside from just changing the main view, which has its drawbacks. Okay, is everyone here? Let me know in chat if you are not here. If you are not in the screen, I can help you out. Yeah, I like the art too. It's pretty cool. Okay, so it is sounding like everyone is here already. And if you are not, no big deal. We just need to get you here. And this is being recorded. So this kind of tutorial for the first time usage of Ltspice will be preserved for all of eternity on my website, or as long as GoDaddy stays in existence. GoDaddy, that's what my dad uses to host his website. Okay. First thing, we're going to go ahead and create our first schematic here. We're going to go File, New Schematic. And we now have a new schematic. This white screen is our new schematic. You may have a gray screen. If you would like to change the background color of your schematic, you can go Tools, Color Preferences. Then you can select the tab for your schematic. You can then change the item to the background, and you can move all the sliders up. Okay, so that color palette editor is in Tools if you ever want to change your backgrounds or stuff like that. I changed my background to white so that it shows up a bit easier on Zoom for everyone. And I'll show you waveforms in the future. I do the same thing. I don't want to get too ahead of myself. But in case you're wondering why yours might be gray and mine is white, it's because the default is going to be gray, I believe. And mine's been modified for viewing. Okay, you have a new schematic now. Maybe not a bad idea to save it before we start making changes to it so that it has a name. You can go File, Save As. Save and Save As are both going to bring up the same dialog box because this doesn't have a name yet. But let's do Save As. Okay. Here's how I like to organize my stuff. Up here, local disk C:. For every engineering piece of software, I create a folder in my root directory in C:, that is called a workspace _ and then the name of the program that I'm using to develop with, in this case Ltspice. So I created one named Ltspice. You can always create a directory by going to a blank area of the browser, right-clicking, and then hitting New, and then Folder, and it'll ask you for a name. Workspace Ltspice. I already got one, so it's complaining about that. No. Delete. I already have one. Okay. What I like about doing this type of structure is that there is no ambiguity as to where my files are being stored. I have tried helping students in the past, especially when it comes to 262, where they have projects created inside of projects and created inside of projects, and it's just a big mess because they were just hitting yes, going with defaults, and not keeping their directory structure clean as they were developing. So this is my habit. And if you come to me with problems of where my files are stored, I'm opening up old files that I thought were new files and I don't know what's going on, guess what I'm going to say? Just organize your stuff from the get-go, right? Create a workspace. Create a directory called workspace. And then put your projects in there. So in this case, I have other things. I have parts that I've created. I've done other things like that. So I actually have another folder inside of my workspace that I call projects, and I keep all of my projects over here. That being said, you can just put your projects and name them inside the workspace. Okay, it doesn't matter. Whatever works for you, but save as and give it a name. I'm going to go into my projects and I'm going to create a new folder. So I just right-clicked on a blank area of my screen. I hit new and folder, and I'm going to go ahead and I'm going to name this Lab 1. And then I'm going to go ahead and I'm going to name my file Lab 1. And then I'm going to hit save, and now I have a schematic file from Ltspice saved inside my workspace folder, right? So if I go to file and I go to open, notice the directory structure up here. C:, workspace Ltspice. For me, projects, inside of projects, lab 1, inside of lab 1, lab1.asc. If I'm going to have a second one, I'm going to go back up a directory. I'm going to right click. I'm going to do a new folder. I'm going to name it lab 2. And then I'm going to save a new schematic to the lab 2 folder. I'm not going to start putting all these schematics inside of the same directory structure because that's just going to lead to messy file organization. Okay? I'm going to hit cancel out of this because we're just going to deal with this first new schematic. Okay, and if you want help with any type of directory structure, organization, or anything like that, feel free to hit me up in an email, show up to office hours. I'll be happy to, share screen with you across Zoom and kind of go over some things, give you my recommendations. Let's get to the real fun part. Okay, we need a voltage source, right? Everyone's good up to here, hopefully. I can't see your screens. If you're not at this point with a new schematic with Ltspice open, now's your time to chime in chat. And my time to drink some coffee. It's cold. Okay. We need a voltage. Right? That was the first thing. We're going to do this schematic over here. We need this voltage source. We need a 10-volt source. We need a resistor, and we need wires to connect everything. So let's go ahead. Let's add the voltage source first. Okay, in your screen, there's a few different ways to do this. You can go to Edit and click on Component. This is going to bring up the Select Component window. Okay, I'll go over that again. Edit menu, Component. A voltage source is a component. Or there's a little button over here. If you hover over it, you'll get a tooltip. And this last one over here that my head's covering, Not anymore. Says component. Left click on that. Comes up with the same exact window. Okay, I'm going to hit cancel again. I'm going to show you something. Edit. Notice in the edit menu, it shows me the hotkey associated with it, F2. So if I escape to get out of this menu and I hit F2, it's going to come up with the same menu. Okay, so you can see all the shortcuts from the edit menu, or you can go ahead and manually navigate your pointer over to the component button, or do it manually from the edit menu. All three methods are going to get you to the same place. Okay. I don't think you can change hotkeys. I may be wrong about that. I've never done it. I've never needed to. So it's a good question though. I'm going to look into it right after. So when you hit F2 or when you went to edit and added component, you should have a list of stuff here by default. How many people do not have a list of stuff here? I know at least one person doesn't. You guys are just being kind. I know someone doesn't. Did I emphasize the unzipping that good that everyone unzipped that thing? Okay. If you don't have a list here, more than likely it was because you didn't unzip that file. That's not the only reason. I'm just saying like 90% of the times that you don't see this stuff here is probably because you didn't decompress the Ltspice zip file. There may be more times. There's a reason that I say it 4 or 5 times, because if I say it 3 times, then I'm going to have about, a couple of people in class. This is the first semester that I haven't had a single person. Okay, so scroll to the end of this component. Voltage. Select it. Master unzippers. Okay, select voltage and hit OK. Now notice your mouse just turned to a voltage. If I left click once on the screen, I now have a V2. If I left click again, I now have a V3. If I left click again, I have a V4, V5, etc. If I want to stop placing voltages like a madman over here, I'm going to hit escape. And now I am done placing voltages. Now I need to clean up these extra voltages. You may be on a laptop, at which point you might have trouble with your function keys. You can go to Edit, and you can click on Delete. Now my cursor changed to scissors. When it looks like a scissors, anytime that I left click on something, it disappears. If I want to stop cutting things out with my scissors or deleting, I hit escape. And now I'm back to my normal cursor. I'm out of the delete tool. Anything that I want to manipulate on my schematic requires a tool. That was the delete tool. If you change your background to black, you're going to have to change everything else to white. Rest in peace. Okay, a quicker way to get to the delete tool is if you have function keys that work at the top of your keyboard, you can hit F5. F5 takes me to the scissor tool. F6 takes me to the copy tool. F7 takes me to the move tool. F8 gives me a hand closed tool. I'll be honest, I'm not quite sure what that does. F4 comes up with a labeling tool. F3 comes up with a wiring tool. You see, all of my tools are accessible across the function keys. This might be more difficult if you have a laptop because you may have to hold like an FN key while you do some sort of contorted three-finger salute to get at those function keys. If you're having trouble with this, everything is accessible from the edit. So if I want to move something, I can select the move tool. Once I have the move tool, I can left click on what I want to move. I can let go and I'm still moving it. I left click again and I'm done moving it. If I want to exit the tool, hit escape. Okay? So that's the basics of manipulating things in this tool. So let's go ahead and I'm going to hit F5, delete V3, delete V2, and hit escape. I am now back at default no tool inside of Ltspice. Okay, so we have a voltage source right now. We need a resistor. To get to the resistor, there's a few different ways. I can go edit and hit resistor. Notice the hotkeys are. I can left click on a resistor, I can place a resistor, I can place two resistors. Then I can hit escape and stop placing resistors. I can also do it from over here, the button for resistor. Left click on that once. Now I'm in the resistor placement tool and I can place a couple more. When I'm done and tired of placing resistors, hit escape. When I want to delete, F5, delete, 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 delete. If I want to move, now here's a good question. I don't know which function key is it. I'm just going to start cycling through these. Oh, there's the move key. It's on F7, right? So that's how I learn which F key refers to which tool. Or if I'm having trouble with my function keys, no shame, go up to edit and go to the move button. And now I'm in the move tool. Left click and then left click again to place it. Okay? Ltspice is an incredibly efficient method of entry for schematics that you are testing. It's probably not what you're used to. It's not as pretty and polished as Adobe Photoshop or something like that. But it is efficient. It is very quick with the push buttons. Okay, we have a voltage source. We have a resistor. We need some wires. F3 is the wiring tool. Or again, go up to edit and hit wire. Draw wire. F3. Okay. You now have these cursors, and be careful because when you get to the edge of the screen, there's a tendency to fly off in a direction kind of quickly. Any place where I see a box is an acceptable connection for a wire. So I can take my cursor, notice because I'm in the wiring tool, all I'm going to have is this big X that moves around the screen. Left click in one box. Now I have a wire that's coming out here. But notice this wire is only going in one of four directions. Up, down, or left and right. If I want to make a 90-degree bend, I'm just going to do another left click. So I go up, left click, across, left click, down, to the box, hover over the box, left click again. Okay, I'm no longer placing wires. As soon as I'm placed it on the other box, the tool turns off from placing wires. So I'm going to go ahead and start the same thing on this other box. I'm going to connect the bottom side of my voltage source to the bottom side of this resistor. So I'm going to start at one of the boxes. I'm going to left click, left click, left click, and left click. And now I'm done. I'm done placing wires, hit escape. And now I'm back at the default mode. Okay, you should be here. we need to give values to the voltage source. We need to give values to the resistor. Let me go back to my schematic. I want 10 volts for V1. I want 5 ohms for R1. Hover over your voltage source. Notice my hand changes. Right click. DC value. This is where you're going to edit the voltage. Notice that the default units is V for volts. So I'm just going to type in 10. And the default unit is volts. So I'm good there. 10 and hit OK. I'm done. Excuse me. Okay. Now I need to set up my resistance. Hover over your resistor. Right click on it. You're going to get a mini dialog box that says resistor. Resistance and the default units is ohms. Change this R to 5. 5 what? 5 ohms of resistance. Hit OK. And I'm good. Now, I'm almost ready to run this. There's one last thing I need to do, which is not something that I do on my paper. I need to pick a point of this circuit and actually tell the simulation tool that that is 0 volts. Okay, this part doesn't need to make sense, but we need to do it for the simulation to work. So don't worry if it doesn't make sense, but we need to pick a point and just tell the program, hey, pick this as 0 and reference everything else off of that. The way we do that is look at this box up here. Hover over it. It's going to give you a tool. It should give you a tooltip. No? There it is. Ground. Okay. So I can left click on ground and I can place a ground anywhere that I want on my circuit. Notice it works just like all of the other placing of anything. It just keeps placing until you hit escape. If you want to delete them, F5. Delete, 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 or delete from the edit menu. When you're done deleting stuff, escape. I need to connect this ground symbol over to whatever point of the circuit I want to label as 0 volts. So I'm going to do that by hitting F3 for the wire tool, left click, and left click. And now I have a nice connection that's been made from the ground symbol to my wires, right? Hit escape to be done wiring. There's other ways to get to the ground symbol. G will also do it. Edit, place, ground, showing you the G next to it will also do it. Okay, either way. Now we're almost ready to run the simulation. There's actually one more thing. We need to tell it what kind of simulation we want to run. Go to Simulate and Edit Simulation Command. Left click on that. There's a whole lot of stuff going on up here. There's a bunch of tabs. We're just going to stick with a basic transient analysis for right now. The stop time, we're going to give it a stop time of 1 second. We're telling this simulation how long do we want it to run for. So I put a 1 in there. Hit OK. And now you're going to have some text attached to your mouse that you're moving around. Don't click anything just yet. Okay. Go ahead and anywhere on your schematic, left click to place that text. It just needs to be on your schematic somewhere. Okay? Let me run through this again. I'm going to hit escape so that I'm not in any tool or mode. I go to simulate and I go to edit simulation command. Left click. The window comes up that says edit simulation command. I enter a 1 for stop time. And then I hit OK. It's going to give me some text attached to my mouse, and I left click to place it on the schematic somewhere. In my case right now, there's no text attached to my cursor because I already placed the simulation command earlier. If I want to change this, if I see some other text, right click on it and the dialog box will come back up. Okay? So if I have some text on my screen that does not say .tran1 because, you know, you goofed up with the edit simulation command, no big deal. Right click on the command and it'll come up with this box. Go back and select transient, give it a stop time of 1 and hit OK. Okay, now let me know if you are not there. I'll give it a few minutes here. So everyone's good? Go ahead and type yes in chat if you're all good. Yees. Yes. Perfect. Okay, awesome. We are ready to run. Simulate and click on run. Your waveform window is going to be black by default. That's okay. Okay, now here's where we can start having some fun with our schematic because the simulation is run. A whole lot of stuff happened. Our circuit was simulated, but it's not telling us anything until we tell it what we want to see. Now we know our voltage source is 10 volts. Hover over your voltage source. Don't left click yet, but notice that my cursor just changed to an arrow pointing downward. Go over to the resistor. Notice again, my cursor changed to a downward arrow. And that arrow has a little circle around it, almost like it's an inspection window to an arrow going through my component. That's my current, okay? If you hover over a current, the default is always, if you hover over a component, the default is always going to be to show me the measurement of current. If I hover over a wire, notice it changes to a probe. Probe is for voltage. And arrow is for current. So let's hover over the resistor and left click once. Notice what we got. A green flat line at 2 amps. Are we surprised at this? No, it was supposed to be 2 amps. Ohm's law told us it was going to be 2 amps. The simulation tool just confirmed it for us. Cool. I love this tool. This is so professional. This is not gimmicky. This is not found in a CD in the back of a textbook. This is professional grade, legit modeling software that I have seen at the workplace over and over again. I've had field app engineer representatives from Linear Technologies, Analog Devices, Maxim Components, all the big name manufacturers use Ltspice to demo their product. If the manufacturers of the components, the high-end expensive components that Boeing and Northrop and all the companies are buying from is using this tool to demonstrate their products to me, then it's good enough for us. It's more than good enough for us. Okay. Let's look at voltage. Now, voltage is different than current because voltage is always measured at 2 points. What did he just say? Why is he saying that? What do you mean voltage at 2 points? Look at a voltage source. I got 2 points, right? This voltage source is 10 volts. I got a point here. I got a point here. What's the voltage here? I don't know. What's my voltage here with respect to down here? Ah, that's 10 volts, right? One side of my voltage means nothing. I need to have 2 points to talk about a voltage. It's a potential difference between 2 points, right? In other words, voltage is always relative to another location. So let me show you something in this tool. If I want to measure the voltage on this side of the resistor with respect to the other side, you see what I'm doing? The voltage at this point of the voltage source compared to the voltage on the other side of the voltage source, what I'm going to do is I'm going to left click and hold. Notice the red probe stayed in place. I'm still holding my left mouse button. I'm going to move this probe to the other side. Notice that it just turned to black, right? I was off of the other wire. I just went onto the wire, and now I have a red probe on one side of my voltage source and a black probe on the other side of my voltage source. Let go once your probe turns black. And now I just took a measurement of the voltage from one side of the voltage source to the other side of the voltage source. In other words, I measured the voltage across my voltage source. I'm going to do this again. Hover over one side of my voltage source. My probe turns red. Left click and hold. The red probe stays. I now have a clear probe. Move that probe to the other side of the voltage source, and now it turns black. Once I have a red probe and a black probe, I've just measured the voltage between 2 points. Let go. And now I have a line on my graph that shows up with 10 volts. Okay, notice that my current just disappeared. Go back and hover over your R1. Notice my probe just changed to a current arrow. Left click once. And now I do have a current measurement, but my head's blocking it. I have a line at 2 amps. Notice my current went into the right side of the waveform window. My voltage is on the left side of the waveform window. The truth of the matter is I have 2 lines covering each other, right? Because they placed the 10 volt at the same point as my 2 amps. This is a little confusing. I can change the scale of any one of these. Right click on, Oh, I'm on the wrong. Sorry, I'm on the wrong window. Oh, I was trying to point with my cursor, but I was in OBS Studio. Okay. So hopefully you guys followed on your voltage on the left, your current on the right. I can always change my scaling by hovering over that scale on the left side, right click, and I can say that my top is at 15 volts. And I can say that my bottom is at 5. No, I want to pick something uneven. 8. And hit OK. Now, check out where we are. Green line is at 2 amps. I know it's my current because if you look in the upper right, it says I, R1. I subscript R1. The blue line is my voltage, V, N001. Okay, what's N001? N001 is the internal name for this wire. Okay, but I don't see the 10 volts on the scale. It's a little hard. So how can I now tell what value this is at? Hover over the V and left click once. You're now going to get an inspection window. And if I hover over my crosshairs in the waveform window, I can left click, hold, and move around. And it'll tell me what is the value on the vertical axis. Okay? So there is a lot of little nuance to this tool. It is very efficient. I know the vast majority of us are probably going to forget the measurement, but we're going to get enough practice with this that we're just going to get really good at doing it. Okay? So if you missed following along towards the tail end, no problem. We're going to go over this again next class. We're going to start on our first lab. Today was a primer. I verified Ohm's law. I showed you Ltspice. I'm very happy. Okay? So we got the loan agreements. Don't forget to order supplies. And I will see you guys on Tuesday. Are there any questions?
I have a quick question.
Yeah, let me stop recording here.